So today we're going to start with our Unit 5.1 work. So work is energy transferred by a force acting through a distance. Okay, so in order for work to be done, a component of the force must be parallel to the displacement of the object. So the force actually has to be in the direction that the object is moving in order for that particular force to be doing work to the object. Okay, so we kind of have two different equations that we use for calculating work, depending on if the force is applied at an angle or if it's just directly applied in the direction of the displacement. Okay, so first we'll start with the force in the direction of the displacement. So we have work, okay, which is measured in joules. Okay, our force, which is measured in newtons, and then our distance is going to be in meters. Okay, so here we have a box that has an applied force of 30 newtons and it has moved a distance of 0.5 meters. So we're going to find the work that was done by this force. So work is equal to our force, which is 30 newtons, times our distance of 0.5. Okay, so we're going to have 15 joules, but we only need 1 sig figs, so 20 joules of work. Okay, for the other equation, we see we have this cosine of theta, okay, and where this equation derives from is the fact that the force that's acting in the direction of the displacement is the adjacent side of our little triangle that we have here. So it would be cosine theta in order to determine the magnitude of that particular component of the force. Okay, so again, work is going to be measured in joules, force is going to be measured in newtons, and then distance is going to be measured in meters. So in order to solve, the work is equal to our force, which is 30, times cosine of our angle, 32, times our distance of 0.5. Okay, so if I put that in my calculator, 30 times cosine of 32 times 0.5, and I got work of 12.7 joules, but again, we're going to include 1 sig fig, so 10 joules of work done. Okay, so notice that the force that's doing work is actually doing less work because the entire force is not directly parallel to the displacement of the object. Okay, so for our next example, a person presses with 10 newtons against a 40 kilogram box that does not move. How much work is being done? Okay, so the key thing here is that the box does not move. Okay, and recall that in order for work to have been done, that needs to travel some type of distance. So because there was no distance, there's going to be 0 joules of work being done in this instance. Okay, for the next one, a box is pulled to the right 3.2 meters with 25 newtons of force. How much work does the normal force do? So if we were going to draw the free body diagram for this problem, okay, we have a box. It tells us that it is pulled to the right, okay, with an applied force of 25 newtons. Okay, it tells us that we have 3.2, or no, sorry, that's the distance, not the mass. Okay, it tells us that our distance is 3.2 meters that it travels. Okay, but the key thing here is that it's asking us how much work does the normal force do? Okay, and we know that the normal force, let me go ahead and switch colors here. The normal force is upward, okay? So if the object is being pulled to the right, okay, our normal force is going to be perpendicular to that. So there's going to be 0 joules of work done by the actual normal force. Okay, so we could determine the applied force, how much work it does, but since it asks for the normal force, it's just going to be 0 joules. Okay, for the next one, how much work is done on a car being pushed 1,550 meters by a force of 3,750 newtons. Okay, so we have a force, we have a distance. Okay, we're going to assume because it's being pushed, it's in the exact same direction as the displacement. Okay, so we're going to have that work is equal to our force, which is 3,750 times our distance. So 1,550. I have 5 sig figs that I'm going to be reporting for this. So when I put this in my calculator, 3,750 times 1,550. Okay, I'm going to get 58,125,00. That is 5 sig figs. Okay, so that would be my work being done by that applied force. Okay, for the next one, a force is applied by a tow truck cable at an angle of 42 degrees from the horizontal. How much work is being done? We're assuming they're meaning that the same amount of force and the same distance from the previous problem was used, except now we have a cable truck or a tow truck with a cable that is at an angle. Okay, so our work is equal to our force times cosine of our angle times our distance, which was the 1,550. Right, so placing this in my calculator, 3,750 times cosine of 42 times 1,550. Okay, again, I'm going to report 5 sig figs. So I'm going to have 4319500 joules. Okay, and again, we see that it is less than what we had here because the force is not directly parallel to the displacement. All right, for our last one for this lesson, how much work is done by the brakes stopping a 12,500 kilogram railroad car going 9 meters per second if it travels 150 meters and takes 45 seconds to stop. Okay, so we have a lot of information given to us here. So let's first start just by kind of drawing out our free body diagram. So I have my railroad car, and it has a mass of 12,500 kilograms. Okay, and it travels 150 meters. Okay, and it takes 45 seconds to stop. Okay, so we know that the force that is allowing the brakes to stop the car is our force of friction. Okay, notice that our force of friction is in the opposite direction of what our displacement for the car stopping is going to be. Okay, which means that our work is going to be negative. So if we were to have plugged it into like our cosine, our equation up here, the F cosine of theta, our theta would be 180 degrees from the direction of the displacement, which would make it -1. Okay, so that's where we get that negative number from. Okay, so we're going to start by determining the force, that friction force that is applied. Okay, so we know that force is equal to mass times acceleration. So let's first determine the acceleration. So remember that acceleration, the equation for acceleration is our final velocity minus our initial velocity divided by time. So my final velocity is going to be 0 because I'm stopping, minus my initial velocity of 9 meters per second divided by 45 seconds. So when I put this into my calculator, I have -9 divided by 45. I'm going to get -0.2 meters per second squared is my acceleration. Okay, and recall that force is equal to mass times acceleration. So the mass of my object is 12,500 times my acceleration of -0.2. So when I put that in, I'm going to get that my force is -2,500. So that's my force of friction. Okay, so when I plug this into my work, okay, and here we've already established that our force of friction is in the negative direction, okay, or we could have used the other equation if we just took the absolute value of this and then plugged it into this equation up here, okay, we would state that it is 180 degrees from the direction of the displacement, okay. So to plug in, I would have my work is equal to my force, which is -2,500 times my distance traveled, which was 150 meters. So when I multiply that out, okay, I'm going to report 2 sig figs, so it's going to be 380,000 joules. Okay, and it's negative work. Okay, so the work being done by the frictional force is in the opposite direction, which is why it's negative. Okay, and then we found the actual value for